Welcome to this class on modeling healthcare systems for advanced analytics in healthcare. Today we're going to be taking a look at transitioning our thought to system type thinking instead of just prediction. Predictive is, focusing on individual outcomes or one thing that we can know ahead of time, where system modeling is this transition to thinking about the overall system and the probable behavior of it. And so that's what we're going to be doing to set the foundation for the next two topics, simulation and optimization. So prediction in systems, we're all probably familiar with. We're trying to forecast some individual component ahead of time so that we can make a better decision. But systems modeling is examining the overall interactions and behaviors of the system in order to describe impact or, leverage points in the system. So predictive modeling, we're going to bring as a tool set when we need to guide individual decisions, sometimes even within system modeling, to be honest. And then system modeling, we bring as a tool when we're looking to evaluate the broader behavior of the system to make strategic decisions or thoughtful operational change and planning. That's kind of the purpose and the distinction between these two. Why do we want to think in a systematic way? I have seen many initiatives fall down because they are trying to force fit these traditional management techniques and frameworks to healthcare. You may see Lean, Six Sigma, or a lot of the quality frameworks for solving problems like PDSA are all based on the presupposition that we have a linear process where we emphasize process optimization. And even if they're not directly presuming that we have a linear process, by how they're solving the problem, they are assuming it because they emphasize process optimization where they're just looking to reduce waste and variation, assuming that this is something that can be stable and controllable. They focus on closed loop improvement cycles that believe that we can, have this cause and effect type relationship between everything that's clear and linear. And this translates well to a lot of areas, especially manufacturing, but it really struggles in complex adaptive systems because that's what we have in healthcare. Usually when we make a plan and standardize within some small area, reality happens right after we do that and when it leaves that area because it's part of a broader complex adaptive system. Now this is a whole field of study in academia that's really interesting, and we're going to borrow some of the described behaviors of complex adaptive systems in order to think about our healthcare system a little bit deeper than just boiling everything down to a strict process that needs to be controlled. We're going to think instead of it as this complex adaptive system, defined as a system made up of numerous, diverse, interconnected agents that adapt, self-organize, and display multiple things like emergence, nonlinear behavior, feedback loops, interactions, these sorts of things. Emergence, we can think of that property as, we can't really predict by studying the individual components. This here is a common experience I have. There's a high census event in the hospital. Leaders come and start asking questions. Did we let too many people in? Was diversion on? Was diversion working? So on and so forth. Maybe they're thinking surgery is to blame. Is it a specific group that's the problem? Is there a pattern that's changing? If you have a thoughtful analyst, the right answer is actually, well, it's more complicated than that. It is not going to be just a single factor because complex adaptive systems that have so many interactions are irreducible. They can't be fully understood by simply dissecting and analyzing its individual components. They also tend to display nonlinearity, which we can think of simply as small causes can lead to large effects. So I have seen many times different variations on this sort of event happening, where we have a very reasonable OR schedule, and our transfer center does not have a large influx of demand, but we experience a weekend maybe of higher than typical ED admits paired with some early in the week low discharge numbers that can lead to something like a dramatic increase in ED borders because these relationships aren't linear. So the small changes in these other two parts can cause a very large change in some impactful area of the system. Another key component of complex adaptive systems is that they have distributed functionality. There's not a single controlling decision maker often, that the system is exhibiting intelligence through this sort of distributed network of agents. So those things together can be helped by advanced analytics. But I would say that they can't be helped very well by advanced analytics if we present ourselves in this way. Some highly technical, kind of overly pompous example of what we do. Hey, we're here to do sophisticated statistics and machine learning using computational techniques to analyze data. When you look at our job that way, you prioritize accuracy of the model, elegance of the model, and you're probably looking at how well we did on average aggregate measures. When what matters to a system that is as complex as that is the workflows and the incentives. And often they don't feel the average day, they feel the outlier days. And that's what actually matters to them, what they need to understand. So to the degree you've been able to appreciate that and work that into your use of advanced analytics, you may have gotten some adoption. A more useful definition that we could bring forward of advanced analytics in healthcare would be that we can think of our hospital system, our healthcare system, our clinic as achieving advanced analytics if we are repeatedly translating raw data into trusted insights and operational change. That's a really different way to look at it because it doesn't emphasize very elegant, super duper accurate models. It says, are we repeatedly taking raw information and turning it into trusted information people can get to an understanding of, and then transition that into operational change. So that takes a really different focus. And so I think it directs us to do modeling to understand down to sort of first principles variation within our system, what explains the behavior within the overall system. And you'd need then to use your models to reveal leverage points in the system instead of just individual sort of predictions. So we're not interested in model count or algorithmic sophistication or the math behind this stuff. The math needs to serve the overall purpose. If we just have this focus of these sort of overly mathematical view of what we do, we're going to do things like individual prediction of case length within the OR setting. And we'll predict cancellations and no-shows for the OR and likelihood of admits and surge predictions for the ED. We might predict demand in our transfer center, census in our hospital, and discharge disposition in our hospital. If instead we're helping the system to anticipate and act on the levers that matter the most, then all of a sudden the connections here really matter. And we actually are probably going to point towards targets like predicting the likelihood of PACU boarding or describing the likelihood of PACU boarding for the purpose of impacting the schedule upstream, or predicting the likelihood of ED boarding for the purpose of adjusting staffing ahead of time. The hospital may still predict census in the same way that we talked about, but we might do it at the service line so that we can influence a diversion decision or focus energy for the discharge teams. We may still predict census at the unit level, but for the purpose of influencing a schedule upstream or directing our cleaning staff to different activity. So you can see this really big shift in focus from the math to the impact. So a few more concrete examples. If you were framing this naively, length of stay you would think of as just that task. But if you were to frame this in a system's way, you'd be using length of stay for modeling and explaining formation of census to understand what operational factors cause the variation and identify where small process changes might help have outsized system impact. In the operating room, you might still want to predict case length for scheduling accuracy if you're thinking of it naively, but if you take this system's point of view, you would be doing it maybe for the purpose of understanding its downstream propagation of the impact, through the OR, PACU, hospital stay, to understand how it impacts the broader system when there's variation in the case length. So the model becomes a map of that cascading effect and not just, an individual piece of information. The emergency department would likely do something like predicted EV arrival volume, but not just for that end purpose, but to model door-to-door admits, to understand a bit about how different arrival patterns can cause different impact to the system. So how are we going to do this? We are going to do this by following a framework, okay? Start by defining the units, map the flow of patients between them. We need to outline our constraints, characterize variation, and then we simulate to measure probabilistic endpoints. And if we're really taking it over the finish line, designing decision support aligned to those workflows. In defining units, it might be as high level as the hospital, but you might need greater detail like our ICUs and PCUs or the individual units. Depending on your problem, you might even need to go all the way down to the individual bed. This will depend on what you need to surface, what you need to understand and inform on. You're thinking outside of just the hospital and what impacts other areas like the ED, transfer center, or OR. Then you're starting to build out different units within this broader system. This is the process of, okay, what matters to my problem? Am I looking at something like the transition from the OR to the PACU to the hospital? And that's what I want to look through with you now as an example, is that sort of transition. If we were just saying what's going on between the OR and hospital, you're looking at just one decision point. There's no real information between there. Unlikely to yield a lot about what happens, what varies in this process in order to cause different effects in the system. More than likely, you at least are trying to understand, okay, from the OR, they usually go to a post-anesthesia care unit, and from there they move into the hospital. That's the way we're going to think through this problem. However, there can be even deeper problems like, hey, I actually want to understand each step in between these two, which is possible. Be wary of, diminishing returns when the question gets this complex or this deep and detailed, but you need to follow your proponents through their problems to understand, okay, are we going to need to model out each of these pieces, or will we stay back at this high level, just OR to PACU, where I'm going to keep you today. After that, we'll talk, after we've got the units that are meaningful to us, OR, PACU, and hospital in this instance. Then we start to think about what constraints exist. How many beds do we have? Are there any limitations on how long patients have to stay in each area? Do we have some nurse staffing ratio we manage to? Those things are going to help us model and decide how will the system react to different scenarios. And we need to code that into our modeling of the system so that when we simulate a potential future, we are infusing reality into it. We are infusing the things that actually impact behavior like this. After that, we need to characterize variation, and we do this through distributions when we model a system. So it is going away from, can we predict how long people will stay in their case, how long the case will take, into, well, let's surface what's the distribution of possible case lengths that happen and what's the pattern that we see from history, so that when we model the future, we've got this reality to infuse into it, that cases tend to take around some average, right? But there are some very short cases, some very long cases. They are less likely, but they do happen. And so we want to model a future where we infuse that so that, in each situation we model, we point to that sort of distribution of what can happen for case length. Same comes up in different parts of this, like, okay, what can happen in the wait in the PACU before they go to the hospital? That there's this distribution of wait that can be very, very long in a few outlier cases, can be very short in a few cases. There's some average that it clusters around, and that's what will happen in the majority, but not always, certainly. We may also look for variation in something like add-on cases. We have a current schedule and know who's coming, but we also know from history that's not everybody. There's emergent issues that flow into our system. People get hurt, and so we can just look back through history and say, 2 days out, how many cases get added on. And we don't have to have a perfect prediction. We don't have to know that answer every time. We can say, here are the different answers from history of how that happened and how they're distributed. Okay, from this point, we've got the units that matter. We've surfaced some history and distribution of what's possible in this translation between the different units. What do we actually do with it? The next few classes are on that. We're going to go through simulation and optimization, but just to give you the intuition, what we do is we model out examples of working through this system. So we look at example current schedules and we pull randomly from this distribution of potential add-on cases. We send them into the OR and we decide how long will their case be by pulling randomly from the distribution of case lengths from history. And then they go into the PACU and we say, how long will they stay there? Well, let's pull on the distribution of previous PACU stays. And by doing that, we can go ahead and simulate, like in row 1 here, we simulated one time, pulled randomly from these distributions of activity. And the result was, in this modeled future, there was a PACU census of 30, and there were no OR backups, let's say. And let's repeat it. Let's do it again. We set up the computer to go and continue to do that over and over and over so that we get to many, many possible futures. And we can see how likely different scenarios within those possible futures are. If we did 100 simulations and we only hit a PACU census of 30 once, then we say the probability of hitting a PACU census of 30 is only 1%. It's a very unlikely event. We're not likely to see that. And if we wanted to, we can even dig into what were the case schedule and the case lengths and the bed placement activity that produced that, just so we can understand what's possible and what would cause this extreme of a value. So that's the sort of output that we're moving towards by working through this framework where we define the units, map the flow, identify any constraints, characterize variation, and get to this sort of probabilistic endpoint. Just a chance to pause and reflect that this is not predictive modeling. Predictive models might actually be used in this sort of work, but they are usually for an individual thing, individual outcome, where these conceptual models are more about analyzing the system and the interactions. And our outputs are going to be used differently between those two types of modeling. So you've just seen how PACU can impact and ripple through the rest of a system and how modeling the system overall can help us think about that. So this approach can be used at the macro or micro level. At a macro level, we might go ahead and characterize the overall hospital in these very high level units, OR, ED, transfer center, discharge, and we would do the same things. We would look for the distribution of how long, let's say, patients stay there to figure out if there's a potential or how likely it is to see delays in transitions from these two units, from the OR to the hospital. How likely it is to see unsafe patient things, patient experiences like boarding or long wait times at getting transferred into the system. We might also do this at a very micro level, like a clinical waiting room area, where we're going to go and figure out the distribution of how long check-in process takes so that we can understand likelihood of different waiting room times and scenarios for patients. Move on to describe how long patients spend roomed but not receiving care yet, so we can understand the waiting for a provider experience for a patient. Because there's a potential to create really long wait times and really poor patient experience. And the waits at different parts or activity at different parts of this flow can amplify backwards through the system, create backlogs and clusters of patients, and really bad throughput and experience can suffer in a big way. Also stressful on our staff. So the core principles you've kind of seen play out in this concept is we're moving to thinking about the system overall and its components. We are trying to look at distributions, not single point estimates, and that the endpoint is probabilistic, not we know the answer. That's what we are doing in this sort of modeling in healthcare. Some final key takeaways to give you before we move on to the next thing, simulation and optimization, are that there can be these complementary model purposes where, predictive models absolutely have their place, but system models just have a different purpose for analyzing, operational dynamics within a system. That healthcare tends to have these sorts of flow constraints that can impact different parts of the system, even though it might not be that part that is impacted that caused the issue. System models help to reveal the bottlenecks within the system, and this is pretty foundational for moving on to the next type of problem solving, simulation and optimization. So that's what I have to share on the topic. Thanks for sticking with me.